Hello everyone, and welcome to this video on reading assembly in GDB. In the video, we're going to be looking at a simple C program where we print hello world 10 times, and we'll look at how that assembles and how to examine memory to understand program execution. So let's get right into it. All right, so this is the C program that we're going to be examining. Let's just go through it. We got an integer I, and then we're printing hello world 10 times in this for loop, and then we're returning 0, and the program finishes. So pretty simple. All right, so let's compile this program. Let me just get rid of this. Okay, let's compile using GCC. Now we're going to use the -g flag. That just includes some extra debugging info and allows us to view the source code. So include that flag, and then the name, which is that, I believe. Awesome. All right, so that compiles nicely. Now let's open it using GDB. So GDB-Q. Now the -Q flag just quietens the introductory info that comes up at the start of GDB. So we'll just put that there, and then the name of the program, which should be that. Okay, awesome. Now let's just type in list. That will allow us to see the source code, which we have here, and allows us to set breakpoints more easily if we need to do that as well. We can also type in dis as main. You could also just do disassemble, or just that for short. And then I'll just disassemble the main function. Something to note here is that this is using the AT&T syntax, which is why we have a lot of % signs and $signs. I think the Intel syntax is more readable, so we're going to use that. You can do that by typing set disassembly -flavor to Intel. I misspelled disassembly. Awesome. All right, so now if I disassemble main again, you can see that we get the Intel syntax, which I believe is more readable. All right, awesome. Let's see what we're up to here. All right, so we're going to set a breakpoint at main. So break main, press enter, and then that's going to be setting a breakpoint at line 5. So here in this for function. All right, so let's start going through the disassembly. So if I type in info register RIP. So this will tell us what's contained at the RIP register, which is the instruction pointer register. That contains the instruction that the CPU is about to process. So if we press enter, it doesn't have anything at the moment because we haven't run the program. So let me actually type in run. All right, so now the program has run, but we've hit the breakpoint at main on line 5 where the for loop starts, and we've stopped. So now if I type in info register RIP, we see that it contains this hex value. If you actually want to see the instruction, you can type in x-i or /i, and then the name of the register with the $sign. And you can see that we get this instruction here. Now, just to review quickly, this x-i, the x command is used to examine memory, and it expects 2 arguments. It expects the location, which in this case is the instruction pointer register, and it also requires how to display that information. We use the I, so we can get it in, we can view the instruction, but you could also, for example, view it in hex. So if I type in x, then we get the hex value that's stored at that address. Okay, so now we've got the register, we've examined the memory. So what's it doing here? So you can see that we're moving 0 into the address base pointer -4. RBP is the register base pointer, and then we're subtracting 4. So we can actually view that address. So if I go examine, let's examine the memory. Examine at RBP. I might need to do that -4. So you can see it's 0 at the moment. This command that's about to execute will 0 it out. Why is it doing that? Well, if we go back up to the top, you can see that we set I equal to 0 on line 5. So this is zeroing out where the I variable is stored. And we can see here that clearly the I variable, sorry, must be stored at the address of register base pointer -4. And if you actually just type in RBP -4, oh, like this, I believe. No, register base pointer -4. Oh, print RBP -4. Print RBP -4. All right, sorry. You get the value of that calculation. So this address here, that is the address of the I variable. So that's pretty cool. You can also use next I. So if I type in next I, that's going to progress to the next instruction. So I believe that's what we're up to. Let me just have a look here. Blah, blah, blah. Yes, let's have a look at the next instruction that executes. So I press that. Now let's see what's at the instruction pointer now. So if I do examine the instruction at the base, the instruction pointer, now we've got the jump instruction. Where's it jumping to? How about we actually examine the next few instructions? So if I do examine -5i, that's going to say examine the next 5 instructions. So we can do that and then type that in. So we're going to get a jump down to this address here. Let's see where that is. If I type in list, not list, sorry. Can I disassemble main again? Cool. So we jump, this is where we're currently at, and we're going to be jumping down to this address. So we've already zeroed out the I variable. Now we're jumping to this address ending in 15AD, which is right down here. Okay, so it's going to come down here and it's going to compare 9 with the variable, with whatever's stored at base pointer -4. So if we're reading that, what would that be? Well, we already know that this is where I is stored, and we're comparing it to 9. So what this is doing is, this is for the for loop, because we're saying that as long as I is less than 10, execute the following instructions. So this is making sure that that's satisfied. So if we actually just go next instruction and run that, and let's see what instruction now we're up to. We get compare it with 9. Isn't that what we just got? Let's scroll up a bit. So we currently got move and then jump. Okay, now we're comparing it. Okay, cool. Sorry, I got confused. So now we've jumped down to here. So it's going to compare 9 with the I variable. And then obviously that's going to be less than 9 because we're at 0 at the moment, as we checked before. So we're going to go down to the next instruction. Let's examine it. And we get this JLE. JLE stands for jump less than or equal to. So that result that was calculated prior, if that was less than or equal to 9, then we're going to get a jump to this address here, ending in 159A. Where's that? That is right over, let's see, 159A. That's over here. So we're going to jump up to this load effective address instruction. So let's do that. Let's go next I, examine the instruction, and now we're at the load effective address instruction. All right, let me make sure we're at the right point. Cool. Okay. So now we're at load effective address. So we're loading this address. Now, what would that be? Well, why don't we examine it and see what it is? So let's examine, let's just say we're going to examine 4 bytes, not 4 bytes, 4 bytes in hex. So that 4 is saying we want to examine 4. We want to examine 4 bytes, which is why we have the B, and we want it in hex, which is why we have the X here. And then we're going to be doing it at this address, 0x7ff666da9000, which is just over here. So let's press enter. And you can see we get these values. Now, it might become a bit clearer if I actually display this in unsigned decimal. Let's do that. Actually, if I just do this, let's do that. Now, if you know your ASCII values, these are actually within the printable ASCII range. So if I actually do examine, now let's examine the characters. If I do C, awesome. You can see that these bytes represent the hello world string. We got the H, H-E-L-L, And I mean, if we just put in, say, we want to examine the next 10 character bytes, you see we get the hello world string being printed. So now we know that this address is where the hello world string is actually being stored in memory. So what the program is doing, it's loading that address into the accumulator register, RAX, and then it's going to print it. So let's go next instruction. Next I. What instruction are we up to now? So this next part, actually, it might be easier if I actually explain it in a chunk. So just a bit of review. We started up here by zeroing out the I variable. We moved down to the jump instruction, which jumped us down to here, where we compared I with 9. So this is part of the for loop. If that was less than or equal to 9, we're going to jump to this address, which is right over here. So that was all part of the for loop. This is now up to the print instruction. We're loading the address where the string is stored. We're doing some move instructions, and now we're calling this address. Now this is where we call the print function and actually print the string. So if I go next instruction again, we get the call. So now if I type in next instruction now, we should get hello world being printed because that's what we're up to. So if I press that, and awesome, we get hello world being printed here. So that's really cool. What are we going to get next? Well, let's go next instruction and see. So now we go back down to the compare. Have we actually added? Did we add? Next instruction, hello world. Oh, I skipped over it. So over here, when I did next instruction, we would have come down to this add instruction, which would have added 1 to this address, which remember is where I is stored. So if we examine that now, we should have not 0, we should have 1 there because we've added 1. Let's examine it and see. Not info, let's just examine in hex, RBP -4, and we get 1. So that's really cool. So we can see the I variable actually being incremented. Why is that happening? Well, remember in the for loop, we get it set to 0, then we got the compare instruction, which is making sure it's less than 10, and now we've incremented I again. And you can see what we're up to now is back to the compare, where we get to compare, make sure I is less than 10. If it's so, complete the next instructions. So if we go back over here, we're back down to the compare. So this is just going to loop because we're in the for loop, of course. Compare it. If it's less than or equal to, jump back down to 159A, which is here. So print it out, compare, compare, and then just keep looping. If you're wondering what's actually stored up at here, this is what's called the function prologue, which sets up memory for the main function, among other stuff. You don't need to really worry about that. And then eventually, once we get to the end of the program, this I is no longer going to be less than or equal to 9. We're going to get 10. Once that happens, this jump less than or equal to instruction won't obviously occur. Won't be satisfied, I mean. And we'll get, what's it called? The program will continue down to the next instruction, which is this move instruction. And this set pretty much just exits the program and make sure that we return 0. All right, so I think that's pretty much all of it. Let's get into a little summary. All right, so let's go over a bit of a conclusion and go over some of the important stuff. So remember that we're compiling using the -G flag for source code access. Remember that we'll also use the -Q flag with GDB to quiet the opening info. Something else to note is that the instruction pointer, which is RIP, instruction pointer, that's the instruction that the CPU is about to execute. We also had the function prologue, which we went over briefly, prologue, which is where the sets up memory for function variables. Let's put down the next line. Variables. Cool. We also have the X command to examine memory. And remember that it requires 2 arguments. The location and how to display that memory. You can also say how many units to examine. So remember, we used the we examined the character bytes using for, or you can examine how many you want. So for example, we did examine. If I do that, that means examine the memory at, let's just say memory address. Examine memory address in unsigned binary. Actually, let me reword that. Examine 2 bytes, display them in unsigned decimal of whatever stored at memory address. That's, I think, how I read it. Cool. Remember also to check our byte order. So you have big versus little endian. So if I actually just quickly go back to the program here, let me open up the terminal. What's a good example I can show to examine this? Let's say that, actually, we can do this with the bytes, actually, at where the string is. So if I do examine, where was that stored? Let's scroll up a bit. Blah, blah, blah. Here we go. So let's say, for example, I want to examine the 4 bytes. So they just say examine in hex, whatever stored at that address. Let's do that a bit larger. Let's say, what if I type in 6? All right, so you can see here that we get it printed out with 0x48, 65, 6c, 6c, blah blah blah. But then if I want to actually examine this memory as if I do as a word is 4 bytes. How about if I do a word like that? So that's going to say examine a word consists of 4 bytes. So examine 6 words in hex at this address. And you can see here that if I have a look at 48, so if you look at we've got 48 here, right? 0x48, but then here we have 48 at the end. Then we have 0x65, and then we have 65 here, 6c, 6c. And you can kind of notice that they're stored, if we examine it as a word, as 4 bytes, they're stored in the reverse order than if we examine them just as bytes, really. Because that's 1 byte here, and that's another byte there. That's because we're using little endianness, where the least significant byte is stored first. So it's important to know what sort of endian, if you're using big or little endian, really. All right, let's go back here. Next up we have, remember next I stands for next instruction. You can also just type it out. Next I is just a shorthand way of saying it. Additionally, instead of doing info register RIP, you can just type in IR RIP, and that'll say that means the same thing. All right, so good job getting to the end of the video. If you have any questions, please post them below and I'll be happy to help, and I'll see you next time.